So I think you're able to see the screen, right? Okay. So we would like to discuss the next topic of the applications of Fermi statistics, namely the theory of diamagnetism. Okay, so this is called Landau theory. Of diamagnetism. Okay. So this was supposed to be the work of Landau in 1930, where he gave a theory for diamagnetism. And it turns out that there is no classical theory for diamagnetism. It is intrinsically quantum mechanical. So let us first try to understand a little bit about the concept of Landau levels. Okay, so first let's talk about Landau levels. Now, if you look at classical picture of, let's say, we have some charged particle, moving in a plane, and magnetic field is applied perpendicular to the plane. Then classically, the charge or the particle moves in a circle. Okay, so this is something which we know. We call this, I think, cyclotron motion. Okay, so now we can ask a question: what happens if you want to study the cyclotron motion in quantum mechanics? In particular, suppose you have an electron, then what happens to the cyclotron motion in quantum mechanics? So let's consider, so let the charged particle be a free particle. Then the Hamiltonian for the charged particle is simply given by p square by 2m. And this is essentially we have px square plus py square by 2m because it is moving in a plane. Without any loss of generality, I consider this plane to be an xy plane. Okay, so now let's say we switch on magnetic field. Okay, we switch on magnetic field. Then we can write down the Hamiltonian. Then we can replace this momentum P by P minus Q times A. But if I'm thinking of if charge is Q, it is P minus Q times A. This is what you call as canonical momentum, and the Hamiltonian is going to be P minus Q times A the whole square divided by 2A. Okay, and of course I have to say that here that I am ignoring the spin. Okay, if spin is there, then what happens? Spin itself is a magnetic dipole moment, and that magnetic dipole moment will interact with the applied field, and that will have a mu dot B like term in the energy. So I'm ignoring the spin. Okay, so what is A? Here A is the vector potential. Okay, and what is the relation of vector potential to the applied magnetic field? B is obtained by curl of A. Okay, so now so let's say that consider charged particle to be an electron. That means Q is equal to minus E, and the magnetic field to be along Z direction, is B times K along Z, and Z is perpendicular to XY plane. Okay, so this is, so the moment we know this, you can write down your A to be equal to half B cross R. This is a uniform field in the Z direction. Then you have A to be given by this quantity. Now you can write down, of course, there is, so you can say that if your B is so A is equal to half, and your B is, let's say, I cap, J cap, K cap, and 0, 0, B, and then you have X, Y, Z. So that will give you that I times Y times B and J times X minus X times B. So you have B by 2 into Yi minus Xj. So this is the A. So far I am not doing any quantum mechanics. This is just I wrote down the Hamiltonian, and Hamiltonian can be written down by, in general, this rule is very powerful. You can use it in even relativistic quantum mechanics. So what you have to do is, wherever P is there, you have to replace by in electromagnetic field and without electromagnetic field. Okay, suppose you have, let's say in, so let's say you have a Hamiltonian given by P square by 2m plus E of R. Okay, in general, you have a Hamiltonian like this. Okay, now apply electromagnetic field. Apply electromagnetic field. Then P is replaced by vector P is replaced by vector P minus Q times vector potential A, and H is replaced by H minus Q times scalar potential phi. So then what happens is the Hamiltonian in the presence of electromagnetic field will be P minus Q times A, the whole square, divided by twice m, plus P of R plus Q times phi. So this is scalar potential and this is vector potential. So any general Hamiltonian will be replaced by this. I have written down a non-relativistic kinetic energy, but even if you have a relativistic formulation, for example, if you say that this is non-relativistic case, suppose let's say that you have your Hamiltonian as C times some alpha dot P plus beta mc square. This alpha and beta are called Dirac matrices. So this is Dirac Hamiltonian, and then apply EM field. Apply EM field. So I use the same scheme here. So the Dirac Hamiltonian in the presence of electromagnetic field is simply C times alpha plus P minus QA, okay, plus beta mc square plus Q times phi. So this scheme actually works always. So in the presence of field, what you have to do is simply replace P by P minus QA and H by H minus Q phi. Okay, so I have used that one here, and I found out this A. And I think you might recall when we did this course on electrodynamics, we made this statement that this is only one of the gauge, and this choice of A is called the symmetric gauge. Symmetric gauge. Okay, so just to recall, we can choose A to be B by 2 into 1 minus alpha into y of I plus minus alpha into x of j. Okay, and you can have this alpha ranging from 0 to 1. So for every value of alpha, okay, so let me call this as A alpha. Okay, so you can choose any value of alpha that will corresponds to a different gauge. Okay, in particular, if you take alpha is equal to 1, then you have your vector potential to be minus, this B by 2 is not there, it is only B. So it is equal to minus Bx into j. And alpha is equal to 0. This A will be equal to by into I cap. So these two are like two extreme cases of this thing, and these are called asymmetric gauges, asymmetric gauge choices. And this symmetric gauge, whatever we have taken here, from here to here, you can go by taking alpha is equal to half. Okay, by taking alpha is equal to half, you can go from this to symmetric gauge. Okay, so let us consider this to be the symmetric gauge. Then we have the following. So let us go back to the Hamiltonian. So my Hamiltonian is going to be equal to Px I cap plus Py j cap. This is my momentum, minus or plus E times y I cap. Of course, there is a b here and by 2 here, and plus this is minus E times b by 2 into x into j cap. So this is P plus EA, and then I have the square of this divided by 2 times n. So which is equal to Ex plus EB by 2, EB by 2 into y into I cap plus Py minus EB by 2 into x into j cap, the square of this divided by 2. So so that is equal to, I will have Px plus EB by m, EB by 2 into y the whole square plus Py minus EB by 2 into x whole square divided by 2m. Now you can see that we can write this as Px square plus Py square by 2m, and then I have plus E square B square by 8m into x square plus y square plus E times B into we have 2 times EB into Px into y. Okay, and then I have minus, okay, the 2 will cancel away because this 2 is there here, and I have minus E times B into Py into x divided by 2. Okay, so now you can see that this particular this particular equation, or this particular term, the third term, you can see that is equal to, if I write down this as EB by 2m into y, okay, let me put a minus sign. I take it out. Then I have xpy minus ypx. xpy minus ypx. But what is this quantity? xpy minus ypx is so if you look at this quantity, this quantity is like your LZ, right? Angular momentum Z. Okay, so I have so xpy minus ypx is like LZ. So I have px square plus py square divided by 2m plus, let's say I pull out half, then I have EB by 2m the whole square into x square plus y square, and minus EB by 2m into like LZ. Okay, so this is exactly like what we have. So this is like a harmonic, two-dimensional harmonic oscillator. Okay, because you can see that this particular term, EB by 2m into LZ, it commutes with this two-dimensional harmonic oscillator Hamiltonian. So you can define something called EB by 2m as some omega c. We call this cyclotron frequency, and so in terms of that, this is like so this much is like 2D isotropic harmonic oscillator. Okay, and so this LZ will actually commute with this Hamiltonian. Okay, so that is something which we have discussed when we talked about, probably not in this course, but when we talked about complete set of compatible observables, we talked about a 2D harmonic oscillator, how the angular momentum LZ commutes with this. So we ask a question that, okay, now if you do quantum mechanics of this problem, then if you try to solve, let's say H psi is equal to E psi, suppose you want to solve this problem, then you can say that you can solve it in the following fashion. So, for example, if you try to solve it in the Cartesian coordinates, then you get okay, so let us put it this way. If you are trying to do this in so you have energy, it will correspond to n1 comma n2, two quantum numbers, because this is a two-dimensional motion, and that is equal to h bar omega c into n1 plus n2 plus 1 and minus something which will, so EB by 2m, and there will be some quantum number associated with this, but that should depend on this. So there may be some function here of n1 comma n2, which we do not know at this moment, but you don't have to, you can get it more directly if you try to solve this problem in plane polar coordinates. Because if you are trying to solve this in plane polar coordinates, then you have this relation. You get this in terms of what is called NL, and this LZ is directly in that case related to L. So essentially what we are getting here is by looking at this quantum mechanics problem. So you have this XY plane. Now in this XY plane, classically you can have any energy associated with this. So you can have any amount of, so you can have your trajectory to be any circle on this plane. Okay, but quantum mechanically, because of this Landau quantization, what happens is that there are some discrete levels. That means, let's say you have some circle, only this is allowed, and then there is another circle that is allowed. So these levels are like discrete energy levels. Okay, so the energy difference between them is so the delta E between these Landau levels is this is a harmonic oscillator, so it is of the order of h cross omega c. So this is what happens. Now, because of this, one interesting consequence that turns out is the following. Like, for example, when we try to look at, suppose, so now let's look at what happens is this kind of Landau levels will happen for all electrons, whether they are free electrons or bound electrons. So this this feature is affecting all systems. Now, what happens? One important thing that we have to understand here is that if you are so when you consider a collection of free electrons, then the density of states that we have, so density of states as we have plotted last time also, this epsilon versus A of epsilon, it has a shape like this, where this is proportional to e to the power half. Okay, so now what happens is this is density of states when we don't apply magnetic field. Now, when you apply magnetic field, I'm still not considering spin, but when you apply magnetic field, what happens is this density of states will have certain singularities. That means your this density of states will be something like it will pick up a peak here, and then a peak here, and peak here, peak here. Like that it goes. It overrides on this, but then there are these singularities. Okay, suddenly it jumps up. This happens because you can have the, suppose if you are thinking in terms of kx ky plane or px py plane where these quantum numbers are there. For a free particle, you can talk about any particular radius k. But now what happens if your density of states is going to be peaking if your delta k is going to contain one of these Landau levels. Okay, so if it is not containing, then you almost don't have any states there. So this so the continuous. So what is happening here is a continuous distribution of states, which are basically points in K space. Are now coalesced. Do not know if I'm writing the correct spelling. Coalesced into discrete Landau levels. Okay, so this is what is important. And now, because of this coalescence of this one, there will be these singularities. And of course, if you have a Fermi energy, this is a metal, then there is some Fermi energy epsilon f here, and there will be a certain number of these peaks before this Fermi energy. Okay, so this is what happens if you have a constant magnetic field. And of course, here I have considered for the discussion of Landau levels, I have considered that this is if B is not equal to B. Okay, so now what happens is you have so now what happens is interestingly you have
Sir,
yeah.
Sir, can you please repeat it once more why the spikes are coming?
Okay. I will come back.
Sir, the presentation is not feasible.
I think I have got some problem. I will come back. Just give me a minute. Is it visible now?
Yes. Yes, sir.
Okay, let me just share one picture that. Yeah. Okay, I think I'm able to do this. So let me just. So what I'm saying is that when you had this density of states calculation, suppose let's say you have you have, let's say, kx here and ky here. Okay, so you always tried like this. Consider a circle of radius k, and then another circle of radius k plus dk, right? So this is dk, and then you try to find out how many number of points are there in this. Okay, so to find out this area, you do it. Area is done as 2 pi k into dk, and then you say that this into volume is the phase space volume. Okay, and then you say that to get the cells, I will divide this by h cube or 2 pi h cube or something. Okay, in k space, you divided this by 2 pi h the whole cube. Okay, so when you do like this, you will get the number of points in this annular region, right? And this is what you call it as total number of states, dn. And then other than dk, whatever remaining is your density of states. This is how we have calculated the density of states. Now you can do the same thing here, but what happens here is that we have these Landau levels. That means this level is allowed. This level is allowed. That means certain k values are allowed and certain k values are not allowed. So let's say these are allowed. So let's say this is kx and ky. Okay, so these are allowed values. So now let's say that I'm interested in finding out the density of states. So let's say I take a k to be this. Okay, and then k plus dk to be this. Suppose if I take this, then in this region, I have all these levels. So I get a very large number. Or in the other hand, suppose if I take my k to be, well, let me draw it a different color. Suppose if I take my my k to be this value here, okay, and then k plus dk to be a value here, such that between this k and k plus dk, there are no such Landau levels. In which case, what happens, I will get a very small, almost zero energy levels in this. And that is why sometimes you get a very large value, sometimes you get a very small value when this quantization has taken place. Okay, Ashlyn, is that clear?
Yes, sir, it's clear.
Okay. Okay. So that is the reason why you get these singularities, and so the existence of Landau levels is something which you have to understand and make